Hello, respected judges. Traditional security completely ignores you after you log in. It is a mere ID check at the front door. So, a hijacker can easily use session hijacking and steal your unlocked laptop, which will result in a catastrophe. In order to solve this exact problem, we have built S.T.R.I.D.E, which is a zero trust continuous authentication product. It is verifying me in real time. It is learning how I interact with the machine continuously throughout the session. Our engine is based on three distinct security layers. The first one is using behavior biometrics. So I have trained the CNN model using six features, that is keystroke flight time, dwell time, mouse velocity, trajectory curvature, click cadence, and error rates. In addition to that, we have also brought in environmental context. So we are tracking real time IP and network routing as well. Thirdly, for the hardware fingerprinting part, what we are doing is we are measuring the physical GPU vector of the machine. So if a hijacker accesses the session using a separate machine, the GPU may be different. And therefore, the GPU vector value will be different. And that is how we are detecting a hijacker. One by one, I will simulate these features. First, I will simulate the autoencoder. So I am simulating a normal user and typing very normally. Right now, the CNN model is measuring my keystroke flight time, the frequency of backspaces that I use, what is my mouse acceleration. Right now, we are in the calibration phase, as you can see. And now we are in the verification phase. I'm typing normally, so the rhythm is verified. In a few moments, I will act as a hijacker and I will act in a different way. So as you can see, the session has been terminated and we are in a sandbox latch. This was the first feature of autoencoder. Secondly, I will simulate an IP attack. So again, acting as a normal user, where my CNN model is continuously learning from my behavior of keyboard and mouse. The second feature that we are testing is the IP hijacking problem. So right now I'm acting as a normal user again. The model is being trained on the behavior of my keystrokes and my mouse movement and the six features that I mentioned earlier. Now suppose the hacker comes in from Tokyo and decides to hijack the session. I go in my console to simulate this and see the system has detected that a change in IP has taken place, therefore representing a session hijack attack. In addition to that, the third feature is uh, detecting the change in the GPU vector. So a hijacker's machine would have a different GPU vector calculation as compared to my hardware. And that is how we are tracing the hardware fingerprinting. In order to simulate that, also detecting the hijack through GPU vector calculation. If the hijacker has a different hardware, the GPU vector calculation is going to be different, and that is how we are tracing the hardware fingerprinting. In order to simulate that, I would again go in my console logs and simulate a change in the GPU vector. So suppose we have the GPU that is utilizing NVIDIA and it has detected a change in the GPU vector and the session has been terminated and we will take the user, we'll take the hijacker rather into a sandbox environment. So now I would like to explain the code base. So about the database, we are using a synthetic database. It has 5,000 rows and six features, as I mentioned earlier. And also, I would like to highlight that we are using sine wave because we have analyzed that human behavior is not linear. Keyboard typing, mouse behavior operates in burst, and that is the exact reason we are using a combination of variance and also a sine wave function to calculate the baseline of normal behavior across the six dimensions. So that is how we are simulating organic human user behavior. So now coming on to sensor.js, which is basically handling the front end portion of our engine. It is basically collecting different physics variables like the uh, mouse velocity, acceleration, Euclidean distance. But then again, these are raw data and raw coordinates that would definitely be useless to our engine. That is the exact reason we are performing feature engineering, and naturally it will increase our accuracy also. So this is the part where we are calculating Euclidean distance and acceleration. So now coming on to the file of train.py, where we have our main ML engine. Here we are also using the concept of Haber sign for our geovelocity concept. What we are doing is we are finding out the longitudes and the latitudes corresponding to the IP address that we are going to get. We are going to find the distance between those particular locations, and with the distance we can put that into the classic formula of speed is equal to distance by time. If the speed comes exponentially high, like 5,000 kilometers in 3 seconds, then this is definitely a major risk factor because you can't travel 5,000 kilometers in 3 seconds alone. We are going to spike the risk rate, and this is going to be a major sign for a session hijacking has taken place. The reason why we are using Haber sign formula and not the normal Euclidean formula is because Haber sign also accounts for the curvature of the Earth, and also we are getting more accuracy with the Haber sign formula. In conclusion, we would like to say that in the whole project, we did not just plug into a pre-made API. In fact, we had to figure out and engineer the whole data extraction process ourselves. We also wrote sensor.js logic in such a way that it captures the keystroke flight times perfectly without lagging the browser. We also dug deep into trigonometric mathematics to use Haber sign formula and not the Euclidean distance formula because the accuracy uh, was not good that way. And we also had to innovatively figure out to extract the vector GPU to figure out the hardware fingerprinting part of the feature. And we can guarantee that every single layer of the zero trust feature in our S.T.R.I.D.E product is built through sheer trial and error. In fact, we can also guarantee that all our features are research based and they are completely accurate. And we have built a product that actually solves a massive vulnerability in today's modern cybersecurity field. And we are absolutely ready to take this hackathon prototype to a real world solution. And we are absolutely ready to scale it further.